Hi, it's Moser with another video, this one on percent yield, part 1, the basics. So first of all, let's see what you should know by the time you're done with this. By the time you're done, you should be able to calculate the percent yield of any reaction when you're given a theoretical yield. And you should be able to calculate the percent yield of any reaction when you're given the mass of one of your reactants. Now, in order to do this, you'll need to already understand the difference between a reactant and a product, as well as understanding how to find the mass of products from the mass reactant. That's some basic reaction stoichiometry. If you're unclear on that, go back to the previous videos. Okay, so let's get started. What is percent yield? Percent yield is really just a way to express as a percentage what you got versus what you should have got. So it's related to percent error, but this, instead of showing a percentage of how far off you were, just shows how much of the material that you should have recovered you were able to recover. Whether that was 62%, 97%, or, ooh, in some cases, more than 100. We'll talk about what that means. Mathematically, percent yield is your actual yield divided by your theoretical yield times 100. So let's unpack that a bit, shall we? What is your actual yield? Your actual yield is what you actually measure. In whatever means you measure it, it's what you actually scrape out of your beaker, slide off your waxed paper, carve out of the evaporating dish, whatever. It's what you actually not only produce, but manage to recover and to measure. Okay, well then what's the theoretical yield? The theoretical yield is what you calculate it should be possible to create, to produce. The theoretical yield is found using stoichiometry. Yeah, reaction stoichiometry, that thing that you've been getting better and better at. So again, your actual yield is what you've measured. Your theoretical yield, if it's not given to you, is what you've calculated based on at least one of the reactants in your reaction. Now, why is there a difference between these two things? Well, good question. There's a difference often between actual and theoretical because of this: ideal stoichiometric calculations. So needless to say, we don't live in an ideal world. Things don't always behave the way we expect, and we're not always perfect. So while we assume that the conditions under which we're running our experiment are perfect, and that every single molecule or atom or ion of reactant is going to react and form all the product it possibly can, very often in the real world, the reactants aren't fully used up. So we have little bits of the reactant left over in the product that we can separate out. Sometimes reactions don't run fully. There's also the issue of loss. Sometimes we don't scrape the beaker clean enough, or sometimes we leave a little bit of extra water in our product and we don't separate that out, so we can have more than 100% yield. In other words, life isn't perfect, but let's look at it and figure out exactly how perfect or imperfect it is. Okay, with this equation, we've got the combustion of magnesium to form magnesium oxide, and we're being told that with the amount of reactants given, which aren't actually given, but we're trusting, with the amount of reactants given, you should be able to produce 157.0 grams of magnesium oxide. If you produce and recover 152.5 grams of magnesium oxide, what's your percent yield? Well, first of all, let's make sure we're clear on the difference between our actual yield and our theoretical yield. I've underlined the two amounts of product that are mentioned in the problem. And the first one is this 157 grams of magnesium oxide. If we look at the sentence that precedes that, it says, should be able to produce. That's theoretical. So 157.0 grams magnesium oxide is our theoretical yield. Our 157 grams is going to go on the bottom, and we're going to make sure we use units in chemical, of course. So that's our theoretical. Well, now what's our actual? Well, here it says you produce and recover 152.5 grams magnesium oxide. That's the actual. That was what was actually produced and recovered. So we're going to put that on the top as our actual yield. I get a raw answer of 96.9426752. It goes on and on and on percent. Now, I'm still bound by the same sig fig rules that I've always been bound by, and each of these numbers has 4 sig figs in it. So I'm going to stop my number right there, and I'm going to round at that 4. That gives me 96.94% yield, which is honestly entirely respectable. What if we use the same equation, but instead of being given our theoretical yield, we have to find it? Oh. Okay, well, if we're told that using 112.5 grams of magnesium in XSO2, you produce and recover 367.9 grams of magnesium oxide, what's your percent yield? Well, we're only given one mass of product. That's this. 367.9 grams of magnesium oxide. The other mass that we're given is the mass of a reactant. So where's our theoretical yield? We have to find it. In order to know how much magnesium oxide we should have been able to produce from that amount of magnesium metal, we're going to have to do a factor label. And as always, we're going to start with our given. I'm starting with my grams of magnesium, the grams of my reactant, and of course I'll have to convert into moles. I've made sure that my units in chemical match here so that I can cancel, and I'm heading into moles of magnesium. My eventual destination, grams of magnesium oxide. What comes next? My mole ratio. I have my mole ratio in place to describe the relationship between the magnesium and magnesium oxide per this reaction. And now I'm ready to go from moles of magnesium oxide to grams of magnesium oxide. Okay, just to do the final checks on my stoichiometry. Units in chemical are the same to there. Units in chemical are the same to there. Those will all cancel. Now, before I do that, don't get carried away, I want to know what numbers I need to put in here. Well, this first box is going to be 1 mole of magnesium is equal to the molar mass of magnesium. My mole ratio comes from the balanced chemical equation, so it's 2 moles of magnesium oxide for every 2 moles of magnesium. And my last is my 1 mole of magnesium oxide to my molar mass of magnesium oxide, which is 40.31 grams. Okay, what's my raw answer? Well, my raw answer, embarrassingly enough, is 186.543, etc. grams. Clearly, there's been a very serious error. But let's go ahead and go with it. This gives me a theoretical yield of 186.5436, etc., and an actual yield of 367.9 grams of magnesium oxide. Oh boy, something went horribly wrong. Oh boy, I get 197.2% yield. Well, obviously something went awfully wrong in the lab. This is one of those cases where if you get a number like this, you need to go back and recheck all your math. In this case, I know what happened. The person who wrote the problem really screwed it up. But when you get a number like this, is it reasonable? No, you can't have produced nearly 200 times what you should have, nearly twice what you should have. What's probably happened is a measurement error for your actual yield or a calculation error. So that's the basics. If you want extra problems for this type of percent yield problem, there will be a few short videos just walking through a few of each. Take care. Get practicing.